All right, today we're going to be implementing logistic regression from scratch in Python. And if you haven't already, I would check out this logistic regression video that I posted on my channel because that will walk through the introduction to the task of logistic regression as well as the solver and the loss function. But in this video, we're just going to implement it in Python, assuming that prior knowledge. But just to recap, the gradient for the logistic regression loss function with respect to the weights is written here. And you can see that you multiply each data point xi, by the difference between the prediction on that data point and the true value. So the more wrong you are in your prediction, the more that point xi is going to contribute to the gradient. And then we have our gradient descent update there. So we're going to be implementing this class, a logistic regression solver, using very minimal library support. I'm only going to be using the NumPy library because that has some useful mathematical operations. And then we'll also, when creating our data set, our playground data set, we'll just use a helpful little function from scikit-learn.datasets called make classification. And this just makes a classification data set according to the specs that you provide. So let's go ahead and define how many of each type, how many data points in our train and test set. So let's, for the purposes of this video, keep it small and just do 4,000 training points, 1,000 test points, xy equals make classification. And then we'll say numTrain plus numTest. So it's going to make 5,000 data points that have a structure that can be learned by something like logistic regression. And then we'll do this very important trick for classification or for any machine learning model with a bias term. We're going to prepend a vector of ones, or we're going to prepend one to each data point so that the weight vector W will have a corresponding bias term inside of it. So here we go, x equals, we'll use the NumPy insert function, insert at column 0 a bunch of ones of shape x dot shape 0, which is the number of rows in the data set, and we'll insert that onto the horizontal. We'll insert that vertically onto the horizontal axis. And then we'll do xtrain, xtest. Here we split the data. And the same with ytrain. We'll create a ytrain and a ytest. Great, and so let's just examine the shape of our data that we just created. So we'll look at the training set shape, and then we'll look at the test set shape. Perfect, so we have 4,000 training points, each with 21 features. And remember, the first feature in each data point is just a 1, which will correspond to that bias term that we're embedding in our parameter vector W. And the same for the test set. And then ytrain dot shape, ytest dot shape. 4,000 data points, it's a binary vector, and 1,000 data points. So just to show you the first 5 entries of ytrain, binary vector, it's a binary classification problem. So let's go ahead and get started. First, we're going to define a sigmoid function, which will be a helper for us. So this is the sigmoid, 1 over 1 plus e to the negative x. And this is just a helper function. Now for our solver, we can put that in a class. So let's create a class called Logistic Regression. And we'll define a constructor, which we use this special init keyword, which will take the self, and then we'll pass in a learning rate to use for gradient descent, as well as a number of steps. And we'll set the learning rate to be equal to this value, and then we'll set the number of steps as well. And then we'll define 3 more class members that will be useful. So first we need our weight vector, W, that will get tuned, but for now we'll just set it to none. And then we'll store our data as well, so X and Y. That way we don't have to pass them from function to function, they can just be class members. And we'll create a helpful function called predict on a single point. And so the point will be called X. And recall that for logistic regression, we run the sigmoid over the dot product of our weight vector and the data point. And that will return a probability. So returns a probability. And then let's define the gradient according to this formula right here. So gradient, and you can see that I prepend these functions sometimes with an underscore. And what that means is just a stylistic way of saying these functions are not intended to be called from outside the class, but only internally. So the gradient will just take self, and then we'll return, it's a sum over all I. So it's going to be sum over something for X in the entire data set. And actually we'll need to get access to our labels as well. So we'll zip self.x and self.y. And what is that sum? Well, it's going to be from the formula above, it's going to be X times self.predict single point. So we'll make use of this function that we just wrote, minus y. Great. And now we turn to the fit function. This is the function that the external caller provides the data, and we will run gradient descent. So let's receive the data into our class member variables. Scroll down here. And then let's initialize our weight vector to random values. So numpy.random.random. And then we need to give it a size. And that's just going to be the number of features in our data. So self.x.shape 1. Number of columns. So now let's do our gradient descent algorithm. For I in range, self.numSteps. Let's get our gradient. So gradient equals self.gradient. And let's do self.w equals self.w minus the learning rate times the gradient. And that's pretty much it, but we can do one slight optimization here. Instead of going the full num steps, we can quit early if the gradient gets small enough where we're not changing that much. So we'll look at the norm of the gradient. So for that, we can use this numpy.linalg.norm function. We can say if that's smaller than some small value, well, let's print format string. You can say exiting after I steps, gradient small enough. And then we shouldn't forget to break. So we can exit early rather than having to go the full number of steps. And that's it for the predict function, for the fit function rather. And every machine learning model should also have a predict function. So create that. And that will predict on a new data set, X new. And then we'll just return self.predict single point X is less than 0.5. So we'll return an integer signifying whether this is true. Sorry, I meant to say greater than 0.5 for X in X new. So 0.5 will be our cutoff threshold for binary classification. So let's run that, and now our class is defined, and let's check out how it performs. So LR equals logistic regression, and we'll pass in 0, 0, 1 as the learning rate for now. We might need to tune this. And then for num steps, we'll put in 1,000. Oh, it has no attribute learning rate. So it looks like we just have a little typo up there. Hopefully that's the only error we have today. Okay, looking good so far. Now we'll do learning rate.fit xtrain ytrain. So pass in our training data, but let's put a little time up top of this cell, and so we can see how long it takes to fit. By the way, this is a Google Colab notebook. If you haven't already observed, it is built on top of Jupyter notebook, but it can be used with Google Drive, and so I think it's just an excellent tool that Google has created. All right, so it took us 1.5 seconds to train, and notice that we exited after 42 steps. So it was kind of crucial that we had this early exiting strategy. Otherwise, we would have trained for a full 1,000 steps. So now let's look at our predictions. And let's predict on the test set, of course. So we'll call predict on the test set. And let's see how many we got correct. So % correct. We'll sum where the predictions are equal to the y test, and this will just return a binary vector wherever they agree. So if we sum that and then divide by the length of y test, that should give us the % correct. Okay, so 0.859, so not bad. And there are little, let's see, so if we sum y test, there are 517 ones out of 1,000 data points. So we can be confident that our model is learning something significant to get 85% accuracy. Okay, so now I should say that you would never in real life create a logistic regression solver from scratch like we just did. You would want to use an already existing library because it will be fine-tuned for optimal performance. And in general, you shouldn't implement something that's already out there. So let's just turn our attention to using an example of a real library, so you have something to take with you away from this video besides creating your own. So we can use scikit-learn's library, and you can get that from the linear model submodule. So let's create our logistic regression model. So LR underscore scikit-learn equals, and they also call their class logistic regression. Now let's call fit on this. So let's fit this on our training data. And let's see how long theirs takes to train in comparison to ours. Okay, so 28 milliseconds compared to 1.25 seconds. So quite a big difference. And that's because the code that they're using is probably highly parallelized, and the optimization method that they're using is probably something a little bit more advanced than just a regular gradient descent like we have here. This library probably makes use of a second order method like Newton's method, which is a topic for another video. Now let's call predict and just look at their performance. So let's predict on the test set. And then let's look at the % correct. So same thing as before, but with the new predictions. See how well they did. Okay, so the same exact performance. So it looks like both of our libraries found the optimal decision boundary. And yeah, so that's pretty much it. So we just, in summary, we created a logistic regression solver from scratch using the formulas that were derived in the logistic regression intro video. All right. If you enjoy this video, I'd appreciate if you clicked subscribe. That would encourage me to create more videos. Thanks so much.